And this is where I guess like the voodoo happens. This is like where all the wacky stuff goes down. All that's happening is basically your node in the input layer is connected to another node in the hidden layer, and those are all connected together. And what you're doing is you're weighting the computer's weighting how much it thinks that pixel is something on a scale from 0 to 1. And it tries to do this in the quickest way possible. So I can show you, we're going to see later, but there's different methods. You can use hyperbolic cosines, you can use sigmoid, you can use all these different ways of getting from 1 to 0 in a very quick way. And that happens all over the place. And the output layer is where your prediction is going to happen. So the strongest weight through the network, the ones that has the highest sum, is basically going to make its way through this network, pop out the output layer, and it's going to print out, we think this is an 8. It's a little black boxy. They call it deep learning, but I don't think there's a lot of learning going on because it's still very active research, like why this works so well. It was supposed to be designed after a human brain. It really knows why it works well. People are getting their PhDs still right now trying to explain why neural networks are so good at what they do. The famous example of it not working well, when Google was first developing this, they were trying to classify wolves and huskies, and so they threw it through the neural network, the same type of neural network I'm going to build here, and it was 100% accurate. Oh, gee, man, we nailed it. What ended up happening was the neural network was just classifying if there was snow in the picture, and if there was snow, they were making it a wolf, and if there wasn't, it was a husky. So you don't really know until you get into the weeds and start printing out what is that node doing. This layer might be thinking, these images have curvy bits. This one has straight bits. So if you want to make a 9, you want a curvy thing on top of a straight thing, and I don't know what the heck that one would do. But I'm not making it 3 layers. You can actually do it with 1 layer, and that's what we're going to do. So I don't know how technically everybody wants to get. I mean, please ask questions later on, but this is how simple it is to build a 1-layer neural network. Input layer, we have 1 hidden layer, and then the output layer. So you can see this is 28 by 28 pixels going in. This is 128 hidden layer. I mean, totally arbitrary. You just pick one. That's what I did. And then the output, 128, why not? It makes the connections a little easier to classify. The activation, this is the weighting function that goes from 0 to 1 to sigmoid. And then we have a way of getting to that sigmoid the fastest. That's this optimizer. So this is invented by Newton. This is Newton's method, stochastic gradient descent. It's, Isaac Newton invented this. So it's an old technology. So what we do is, here's the model printed out. Basically what you do is you take the model, you fit it on your testing and training sets, and you just let it run. And you let it run and let it run. This is where the heavy computation comes in. This took maybe 25 minutes on my laptop to run. If I added more layers, it would take a little longer, but 5 minutes isn't bad. Just a little code to see how well it's doing. You can see that the training set and the testing set, they converge pretty late. It takes about, right about 20, it takes about 20 runs through the data to get to where you have really good convergence between the training and the testing set. And we can look at the predictions. So if you remember, they're from 0 to 9. So we can print out the predictions of what we think the neural network is going to tell us. So they're all pretty low until you get to this guy, which is 87%. So that's what it's going to print out. We look at it, we let it go through a few counts. So it's 0, 1, 2, 3, 4, 5, 6, 7. And the prediction predicts a 7. That's cool. It's going to take a long time to guess and check each one. So we can do what's called a accuracy score. We can see that the neural network is predicting at 86%. It's getting 86% of the handwritten digits perfect. We can even go further and look at where it's making a mistake and where it's getting them wrong. This is a confusion matrix. So it took each one is different depending on what language you use, but the columns are what the neural network is predicting. The rows are what it actually is. So here you can see that it predicted it to be a 2, and it was a 0 4 times.